This is the next subsection of the introductory notes to digital ASIC design. We'll explore an example of an ASIC-dominated product, showing how important ASICs are within that product. And I'll go over the basics of an ASIC design flow. Here, for example, is the BlackBerry Bold. This is a teardown provided by Design Electronics. And this first page just gives a summary of the capabilities of the mobile platform. The second page here breaks down the mobile platform by various structures, for example, total costs on the bottom left-hand side by function. As you can see, the total cost is well dominated by the integrated circuits within this function, within this product. And of course, you can see other subproducts here, including cameras, electromechanical, and so on. Here's a complete list of all the components within this mobile platform. And I'm not going to go through these in any detail, but if you look through them, you can see a lot of them in integrated circuits. And just about all the integrated circuits would have a digital component to them, even if they're not ending, and they might even be totally digital. For example, about halfway down the page is the communication processor from Marvell Technology. Obviously, this has some analog functions to it because it has some RF functions to it. But in addition, you can see it has integrated baseband, and the baseband processing will mostly be done using an ASIC submodule within this integrated circuit. This shows the component types listed by contribution to the total cost of the system. And as you can see, the cost of the system is dominated by the cost of the logic parts, the ASICs. You can easily see this in the sum of total component costs on the right hand side. It is almost half of the total cost of the system. So you can see that even though there's a lot of capability provided by these logic ASICs, that capability is well used and still dominates to a large degree the cost of these systems. Even one like this, which mostly has 4 radios in it. Next, I want to talk a little bit about the ASIC design flow. Here's a high-level summary of the major steps in an ASIC design flow. If I was going to list all the steps in detail, it'd actually be quite a long list. A typical ASIC designer, or typical ASIC design group, uses 40 CAD tools, from initial design capture through to final verification and tape out of the structure. The first major step in the ASIC design flow is the high-level design. And we're not going to talk about that much in this class, but it includes specification capture and simulation, often at the specification level. For example, using System C is a common way to do this. And in fact, one of the successors to this course at North Carolina State University is EC 720, which discusses how to program things efficiently in System C. One thing that has to be decided at this phase is the hardware-software partitioning. And of course, also IP selection. Modern designs use a lot of pre-existing designs, often referred to as intellectual property. The next step is the next level down design, RTL design, the register transfer level. Though it would be lovely to be able to go straight to logic from the high-level description captured in C or System C, in practice, though it is possible, in practice, the logic that's produced is very inefficient. So there needs to be a second phase of detailed RTL design, which of course is a major topic of this course. Then of course we want to know that the RTL is correct and of course produce a synthesized gate list from it. So there's a lot of verification that happens, particularly logic verification, to make sure the RTL is correct. Then of course there is synthesis to a gate net list. And the parts I've talked about so far are often referred to as the front end of the design because they're not dealing with any mask level information. The rest of the design, often referred to as the back end, is largely towards the goal of generating and verifying the masks that then go to fabrication. So next step 4 here is physical design. That is floor planning, place and route, and clock tree insertion. And then there's a lot of time spent on performance and manufacturability verification. That is, does the timing work, including the actual delays of the wires? Signal integrity refers to that the noise levels are not too high, for example, due to crosstalk. Power integrity, you're worried about the impact of large current draws on your ability to deliver that in the power network. Design rule checking and electrical rule checking refer to are the details of the layout such that the end product will have a high yield. So this is just an overview of the ASIC design flow, and again, the main subject of this course is RTL design and synthesis. So most ASICs, including FPGAs and gate arrays, are designed using an RTL synthesis-based methodology. The idea is to capture a simulatable description of the logic at the register transfer level. That is, all the registers are identified and named as I emphasized in the revision section. Simulate this extensively to verify correctness of the design, and then go to logic synthesis. So on the bottom right there, I'll give a small example of a Verilog module specified at the RTL level. We'll come back to this particular example later in the class. Later in the course, more precisely. Then we want to turn that RTL into a gate level description. That is, AND gates, OR gates, flip-flops, and so on. This is also verified for correctness, actually within the synthesis tool. The output of this step is often referred to as a net list. That is, it lists all the nets, the wires, and how they're connected to all the gates. On the bottom of this slide, on the left, I've given an example of a textual description of a netlist, actually in Verilog. You can see we have the name of the standard cell, for example, NOR2 or NAND2. The 2 refers to the number of inputs. The name of this particular instance of the cell, for example, you can see here there's 2 NAND2 cells. One's called U37, one's called U38. They have to have different names. The dots refer to the ports inside the cell. The Y port is the output, A0 and A1 are the inputs. And the value in parentheses is the net in the netlist, the name of the net in the netlist. You can see, for example, here there's a net called N109 or N103. And if you look, for example, at the net N109, it comes out of the NAND2 U37, and where does it go to? It goes to one of the inputs of the NOR gate, U36. So this netlist implicitly describes how the gates are wired together. Some of the nets here are named /value. Value is actually a variable that was in the RTL, whose name ended up being preserved in the detailed netlist after synthesis. On the bottom right, we have a schematic that corresponds to the netlist. After producing a netlist, we then want to turn to physical design. There's 2 major steps here, floor planning and placement followed by routing. The floor planning phase, a designer might input a floor plan such as on the top right. This gives the general idea of where each function is going to be. In this example, we have a dual processor unit that we designed as part of a 3D project that's integrated with a cache. In placement, the gates are arranged in rows, and I described earlier in the previous submodule how the designs of the standard cells are such as to accommodate this easily, because they can share power and ground rails. The bottom right shows the floor plan after place and route. You can see here the nice neat boundaries on the top right that the designer's intent are lost as the actual tools try to efficiently use the silicon area. But the general intent is still matched. After placement, but before routing, we do clock and buffer insertion. This is usually as a dedicated tool and dedicated designers, or at least semi-dedicated designers. In the next set of notes, we'll talk about clock distribution, but this requires insertion of a lot of buffers and a lot of wires in order to distribute a clock across the chip, and that is a CAD tool that we won't be seeing. After that, we do the routing, which wires all the logic cells together. I'm not going to go through all the steps in the back end, but I do want to very specifically talk about one step that integrates both back end and front end, and that is to do with timing verification. The delays of the wires are a very important part of the total delay within the netlist. Obviously, the delays in the netlist consist of both logic gate delays, which are largely determined by the standard cells, and wiring delays, which are of course determined by the lengths of the wires that you end up with connecting the standard cells. So to get that information, we have to actually what's called back annotate information from the actual layout. In this example, there's actually two things that are back annotated. On the right hand side, and the second bullet down, we have the back annotation, the details of the clock tree synthesis, i.e. what's the clock skew, and we'll talk about that in the next set of notes. And you can see beneath that, we're back annotating the wiring parasitics. This is referred so the wiring delays can be accurately calculated. And this sort of integration between the front end and the back end is needed in order to produce accurate timing, and thus be really sure that we're not going to get timing hazards in the design, as we discussed in the timing section in the next set of notes. So thank you for listening to this sub-module. I would ask you now to please do the sub-module quiz before proceeding to the next and final sub-module for this introductory section.